Okay, welcome everyone to this final 1A session of FRB 2021. This is our first and only late breaking news slot, and we are going to have 5 talks during this slot. All of them but one will be live, and even for the recorded talk, the speaker is online, so we will have plenty of time and opportunity for questions and discussion after each of these talks. I expect that they will all be very interesting and engaging, and I'm sure discussion provoking. So if you would like to interact after the talk, use the Q&A feature in the Zoom. And we also have a late breaking news Slack channel in the Slack if you'd like to interact there as well. But I will be monitoring the Q&A and the chat after the talk to moderate the questions. So we can get started straight away. And our first talk is going to be by Dee Lee about FRB 190520. So take it away.
Thank you. Thanks, Emily and Jason and the organizers for this opportunity to report on this recent discovery. And it seemed to be the hipper and the weirder brother of 121102. So 190520 was discovered during the so-called conventional radio astronomy fast survey. With fast in drift scan mode, we record 4 data streams simultaneously, namely H1 imaging, galaxies, pulsar searching, and transient, particularly fast radio burst. This was enabled by a novel high cadence Cal injection technology, which realized this unprecedented commensality between basically H1 and pulsars. And the first new discovery of FRB was published by Wei Zhu last year. So this source has a DM of 1800 and has a triple peak structure. We haven't been able to catch any repeating burst. Now, if we put the fast discovery in the context of all published FRBs, it's nowhere near being competitive in terms of number of discoveries with, say, the wonderful CHIME. However, they does occupy a unique parameter space of dimmer and presumably more remote or very active low energy bursts from nearby repeaters. And with a few more discovery in the pipeline, and the most notable of which is 190520, which was discovered by Chenhui Liu. So when he processed the initial discovery scan, there's already multiple bursts within seconds. So the first burst come after about 3.3 seconds. The second come after the first, and the third one come 10.1 seconds later. So the point source transit time of a single fast beam is about 12 seconds, and then 20 seconds later, another burst, presumably of the same source, comes through a different beam. And this multiple detection in 2 beams allow for an initial localization of about 5 arc-minute. And in the ensuing follow-up campaign by FAST, 190520 is just like the Energizer bunny that we detect at least 1 burst in almost all 1 to 2 hour follow-up sessions. So that resulted in more than 200 pulses in about 25 hours. And the total DM of 1200 correspond to a excess DM based redshift estimate of 1. And the initial localization allow for a further localization, and this has been realized by the wonderful real fast system on JVLA. So we were lucky enough to catch a burst from the first session in early July last year, which detect both the burst and a co-locating persistent radio source. And in the following weeks, the initial redshift measurements were made by Palomar, which has a redshift of 0.24. And the source was then followed up by Subaru, CFHT, CAC, Swift, and Chandra, and a slew of other radio telescopes. So if we look at the composite image of the host galaxy, both the PRS and the burst seem to be located in the peripheral of the galaxy, and the burst and the PRS are co-located. So the ellipses are the burst location with one sigma arrow box, and the crosses are the PRS. So they are largely consistent with each other. And we do have to look further into the galaxy, particularly the initial redshift measurement with a slit position going through only the core of the galaxy and a foreground source. Fortunately, we got some CAC time. Now we can position the low resolution imaging spectrograph with a nearly orthogonal slit position, but still get a consistent emission spectrum. And this emissions spectrum cover both the core and the peripheral of the galaxy, and they are consistent with each other. So now I think we have a secure identification of the and the localization of the corresponding galaxy at a redshift of 0.241, which is much smaller than the one based on DM axis measurement. And if we just look into the configuration, so here is the burst and the galaxy, and it does reminiscence of nearby dwarf galaxies. So this is NGC 1140 of roughly the same physical size. It's just much closer at about only 20 megaparsecs away. And the notable feature is this chain of giant H2 regions representing recent star formation, and that seem to really worth further exploring for, say, similar situation regarding the burst, 1905-20. And now with the line of sight and the pointing relatively secure, we do have to consider the possibility of the burst being much further behind and just happen to passing through this foreground galaxy. And using the magnitude, particularly the J-band magnitude and the source density, we estimate a chance coincidence probability of less than 1%. Furthermore, if the burst signal does pass through this plasma lens with a substantial electron density, then we estimate a much longer scattering timescale that should be in seconds rather than in milliseconds, which was derived the real burst. So we can utilize this slightly intimidating formula from JIM, and the key factor here is the geometrical factor. Basically, if you put the light source much further away from the lens, you have a much larger geometrical factor than it's located within the host. And for a much better explanation, please see Stellar's excellent talk yesterday. So in summary, based on multiple bursts detecting in 3 bands by VLA in about 11 hours, and the optical follow-up with both CAC low res and Palomar double spec, we now have a robust identification of the host galaxy at redshift 0.24, which translated into an estimate of DM host about 900 PC per cubic centimeter. That's by far the largest local host DM that has been measured so far. The persistent radio source is also co-located. It has the even lower chance coincidence at only a few parts in the milling. And the persistent radio source has a flux similar to that of 121102, slightly brighter in L band, which if we attributed all to star formation rate, is much higher than the estimated star formation rate of 0.4 solar mass per year. So this, I think this further strengthens the case that the PRS being compact and brighter is actually associated with the bursting origin rather than the star formation in the galaxy. By the way, the 0.4 solar mass per year is above the main sequence, but on par with star-forming dwarf galaxies. Now, if we put 121102 and 190520 together, they do have many notable sort of characteristics, and it's deviate from the general population. If you look at the waiting time, in terms of tens to hundreds of seconds, that peak can be fully expanded by a stochastic processes. So we have rule out basically periodicity between 1 millisecond to 1,000 seconds. And on the short time scale of a few milliseconds to a few tens of milliseconds, there is a significant, statistically significant clustering. If you look at the energy, there's this clear bimodal distribution, and it's hard to say for 190520 because the number of bursts is much smaller, and also it right now only cover about one deck. On the other hand, the 121102 data set already cover 3 orders of magnitude in terms of energy range. However, we do start to see the same characteristic energy below which the burst rate start to decrease. And I think that is in contrast to the simple power law phenomenon, and I think it's a general trait for active repeaters. And they are all very different from SGR J9035. So after the giant burst, for a period of a few months, it's basically a regular, not say regular, it's regular pulse emitting pulsar. It has clear periodicity and it has this behavior both in waiting time and phase space. So if we now put 190520 in the DM and redshift plot, and Xiaomi made this plot with the presumed McCourt relation and the cosmic variance. And there is already, with all known well-located sources, there's already a hint of a long tail. And with 190520, this really go to the extreme. So this is saying that for this particularly active repeaters, it's probably will be hard to characterize or using this relation directly to probe the baryonic matter distribution without really carefully characterizing the local host galaxy.
3 minutes.
And okay, and 121102 has famously this very large RM, and it's changing. It has the compact PRS and large local host DM, and so does 190520. So I don't really have time to go into the RM, which is only in the initial processing stage, but they are all indicate that such active repeater tend to be in complex local environment. So the complex local environment, high repeating rate, PRS, they indicate 121102 and 190520, such active repeaters, either they are of different origin or they may be at an earlier stage of evolution of a general population. So I sort of only sort of go over the basic facts and the surface of a lot of work by a very active collaboration. So we have still have monitoring campaign at FAST, and we have one epoch of observation at Effelsberg and EVN that we are seeking to continue in this semester. And of course, JVLA, GBT, VLBA, parks, and optical and high energy instrument. So the source has been detected by FAST, JVLA, GBT, VLBA, and parks. It has this notable features, there's no periodicity. It has about a 10 millisecond scattering time scale, prominent scintillation, and a identified redshift of 0.241, much smaller than the DM access redshift. So just to sort of rehash the main highlights. So it's high DM host. It's the second confirmed association between the burst and the compact PRS, as I also, which is also supported by its bright flux, its identification in both VLA and VLBA, and it's extremely active. So now we have one source that beyond 12.11.02, I think, was more sensitive follow-up by FAST and other instruments, and particularly also by this wonderful and ever-increasing sample provided by CHIME. We may expect more such source to be reviewed, and we are going to see this either a unique population or this early stage of evolution. Thank you.
Very nice talk, very interesting results. I said, wow, already on like the third slide. So it's very cool. Questions are already coming in as expected. So I will start from the top. X is asking, he says, wonderful result. Did you make an interesting, point about the implications for DM cosmic inferences? Does your DM host estimate conflict with the log normal PDF estimated by previous studies?
It does. It's just very extreme since it has a total DM of 12,000, and the vast majority of it is in the host. So it does, for such sources, you does have to look into the galaxy itself.
Yeah. Okay. Next questions from Ron Eakers. Is it significant that the two dwarf irregulars with large excess DM, UR 190520 and its Arecibo sibling 121102, are both discovered with the most sensitive telescopes but small field of view? So is that significant?
I think that's not a pure coincidence, since from the very start we know, say for FAST, but I think it's technically similar for Arecibo, that one, we are not competitive in terms of blind surveys. So once we found a source, or someone else, a CHIME found a source, we do immediately sort of scheming for deep follow-up. And it happened to be that they exist such sources that just have, that's been very active and has many much weaker bursts.
Yeah. Okay, next a question from Matthew. Maybe this is for everyone in general. What was the scattering time for 121102 at the same frequency?
So in L band, it's about 10 milliseconds.
For 121102.
Oh, 121102.
Yeah, so that one I don't know off the top of my head.
Yes, I can check Xiaomi's wonderful paper. I think it's of similar similar magnitude.
Yeah, if someone has the number off the top of their head, they could put it in the chat. But we'll move on because we want to get through some questions. So the next one is from Brian Gainsler. Wonderful result. What does the radio spectrum of the persistent radio source look like? Is it similar to that of 121102?
Yes. So thanks for asking. I have it back. So I didn't show this because the 121102 is much better characterized. And you can see that it has a turnover of new F new at about 10 gigahertz. Unfortunately, I only have the F new plot, which seem to basically, if it times new, it will be flat around L band. It probably has a lower turnover frequency than 121102, but you can see it's varying and it's need further characterization.
Nice. Okay. We have time for like one or two more quick questions, and then we'll have to move it to maybe Slack. So let's see. Vikram says, do you have a chance association probability for the PRS and FRB, and also for the PRS and the host galaxy?
So for the host galaxy, we use the J band magnitude of about 22. So that's about 1% to within a 0.25 arcsecond. For the PRS, the source density is much lower. And with the same arrow box, the chance alignment is only, say, 6 parts in a million.
Okay, great. And then final quick question from Susumu Inoue. How much of the host DM can be something more local to the source rather than associated with the host galaxy?
Oh, that is hard to say, but we favor that it's more localized to the source for two reasons that I have mentioned. One is that the PRS luminosity corresponding to a star formation rate about 20 times higher than the measured rate for the galaxy at 0.4 solar mass per year. So this is saying that the flux of the PRS should mostly come from that event or that site, but we can only localize the site to hundreds of parsec at the moment. And the second is that it does seem to be a compact source at, say, 0.1 arcsecond.
Okay. All right, so we do need to move on, unfortunately. So thank you, Dee. That's a very interesting talk. Who is going to be telling us about the detection of circumgalactic gas with FRBs. Take it away, Liam.
Thanks a lot. So yeah, I'll be talking about this result that Vikram, Ravi, and I have been working on quite recently, and which we put online last week, where we've detected circumgalactic gas using FRBs from the CHIME FRB Catalog 1. And I think the previous session set the stage for this quite nicely, particularly Sunil and Amanda's talks. But the basic idea is as follows. You have some distant fast radio bursts. Some of them will intersect foreground galaxies, the dark matter halos of which are full of diffuse gas that's otherwise very difficult to detect, but will imprint various propagation effects on the FRB, most notably excess dispersion. So in the past, it was assumed that you would probably need quite good localizations for a large set of FRBs to do this. You would look for the signal statistically, and because the optical depth to the foreground galaxies only gets appreciable for really distant galaxies, you need to localize the FRB to such a small localization region that it's comparable to the halo size. And if the halo is at redshift 0.3, for example, you need quite good localizations. And of course, CHIME FRB is maybe 10 or so arc minutes by 10 arc minutes. So with this in mind, Vikram and I thought we could try this for galaxies in the local universe within, say, 50 or so megaparsecs, where the angular size of an L-star galaxy's halo is at least comparable to the CHIME FRB localization region. So for this, we use the gravitational wave galaxy catalog. This is fairly complete. It includes galaxies out to 100 megaparsecs. Just doing a quick calculation, you find that if you want to use most of the CHIME FRB localization regions, you might want to limit this to about 40 megaparsecs. So we take a cut like this, shown in the red dots, where we've also excluded absolute blue magnitudes greater than minus 18.5. And these are the CHIME fast radio bursts. The color indicates their dispersion measure. And so we're going to take these two catalogs, look for galaxy FRB intersections, and then ask, is the dispersion measure of the intersections greater on average than the non-intersecting FRBs? So the optical depth of a Milky Way-like galaxy's halo out to, say, 50 megaparsecs is about 0.05. So you might expect 5% of sources in the CHIME FRB catalog to intersect a foreground halo in the local universe. And this gives you a couple dozen intersections. And this is the curve from the actual data where B-perp is this threshold impact parameter. So if the source comes within an impact parameter less than B-perp, we consider it an intersection. And this curve grows quadratically, as you'd expect. Now, if you choose one of those values, so suppose you set it to 250 kiloparsecs, you get a couple of dozen intersections, which you can see here. So here, the little blue dots are all of the CHIME FRBs that do not intersect a foreground galaxy. And they're color-coded by the average dispersion measure of that subset, which is about 600. The larger gray circles are the foreground galaxies that have been intersected by a CHIME FRB, or which have likely been intersected. And their size corresponds to the angular size based on our model of their mass, and therefore virial radius, and of course their distance. And one thing you'll notice is that more than half of the FRBs that intersect a foreground galaxy intersect a galaxy that resides in a group. Okay, and this is expected. Roughly half of galaxies live in groups, but this is relevant later for interpretation. So this includes the local group, M33, M31, and the Milky Way, the M74 group, and M81 group. Okay, so now we want to ask, do these intersecting FRBs have a statistically significantly larger mean DM than the rest of the population? So again, if we freeze B-perp at 250 kiloparsecs, we get DM distributions that look like this. Green is the foreground galaxy intersection, black is the rest. And we look for differences in the mean dispersion measures of the two distributions using a two-sample t-test. So this is explicitly designed to look for differences in means. And with this particular B-perp, we get a p-value of 3% and a larger mean DM of a couple hundred units for the intersecting. Now, this is just one choice of B-perp. So if we do 200 kiloparsecs instead of 250, we get this, a p-value of about 1%. And if we set it quite small to 150 kiloparsecs, we have fewer intersections, of course, but we still get a p-value of about 10 to the minus 3. And in all cases, there's excess DM for the intersecting halo galaxies. Okay, so we can actually plot this as a function of the threshold impact parameter. This black, thick, dotted curve are the p-values that we get when we choose different slices or different criteria for an intersection. So this is B-perp on the x-axis in kiloparsecs. And you see that below about 350 kiloparsecs, we get a statistically significantly larger DM. So p-value is less than 0.05. And what you see in the background, the sort of lighter curves, are a jackknife test where we've randomly shuffled the dispersion measures, although kept the same locations of the FRBs, and then run it through the same cross-matching code and asked, do you get statistically significantly different DM values for those resampled FRBs? And the answer is no. In fact, to get DM values that are as large as the actual data, you have to do a lot of realizations. So what you see on the right here is just a cumulative distribution for a couple hundred of these reshufflings, where we've averaged p-values between 100 and 300 kiloparsecs, and said, do any of those average p-values, are any of them lower than the actual data? And the answer is no. So this, even though there are 10 or 24 intersections, depending on B-perp, these DM values are really exceptionally large. So this tells you the statistics of the difference in the means of the two distributions, but we can also look at the size of the effect. So here's DM excess as a function of impact parameter. So you'll notice that the variation in the curve is a lot smaller than the error bars, and that's because the points in B-perp are very correlated. They correspond to overlapping sets. But you see that there's a larger than expected DM excess. Naively, if you asked me like 3 weeks ago or 4 weeks ago, how big this excess would have been, I would have said 20 or so units of DM, and that's in line with most simulations that I've seen. So we can talk later about why this excess is larger than expected. Now, because the signal was large and because it really does appear to be quite statistically significant, we wanted to try to do various tests and cuts and resamples on the data, trying our best to make the signal disappear effectively, or try to find selection effects that we might have been fooled by. So in green are tests where the signal remains, and red are where the signal goes away. And in each case, if we expect it to disappear, it does. And in each case, if we expect it to stay, it does. So for example, we vary the absolute blue magnitude threshold for GWGC galaxies. So between about -17.5 and -20, the signal remains. If we do different max distances between 15 megaparsecs and 50, the signal remains. If we only use galaxies that are farther away than 50 megaparsecs, the signal goes away, which we expect because they become small enough in angular size that you're just getting false associations. So the FRBs highlighted as having intersected the galaxy probably didn't actually, and therefore you don't expect them to have excess DM. With the CHIME FRB catalog, we did various things like use different values for the dispersion measure, the observed DM, DM minus NE 2001, minus YMW. We did different galactic latitude cuts, as well as different selection criteria for whether or not the FRB actually intersected a galaxy. So doing a confidence weighted test where we actually use the position contours provided by CHIME FRB. We use the maximum likelihood position, and we also turned off the sort of virial radius scaling that we were doing from the galaxy's mass. And then I already mentioned that when you scramble the dispersion measures or you scramble the positions, the signal goes away as expected. Okay, so I mentioned that the signal appears to be larger than we expected. The excess seems to be of order 10 to the 2 units. And so this is just a simulation where you take a field galaxy, a lone galaxy, and its CGM with 2 different models for the electron distribution, modified NFW in orange and a beta distribution in blue. And you just intersect it along random sightlines with of order the number of intersections that we had in the CHIME catalog. And you see mean values of about 30 to 40 parsecs per cubic centimeter. Granted, there's significant variance in the distribution and fat tails in the case of MNFW, but still, these are tens of units, not hundreds of units. And again, this shows something similar where you actually do a weighted average over the CHIME localization region and then produce a DM histogram from that. Okay, so how do we explain this? If the signal really is of order 100 units of excess DM, well, one way to do this is just to have bigger dark matter halos. So for example, if you have a galaxy residing in a group, which has an intergroup medium, and the group's halo mass is between 10 to the 12.5 and say 10 to the 13 solar masses, you can most definitely get DM offsets of order what we're seeing. And remember, I mentioned that most of our intersections are with galaxies that reside in groups, and actually half of our intersections are with the local group itself. So if we just cut the data up such that we only include the local group, we see that actually a lot of the signal comes from M33 and M31, which subtends a really large angle on the sky. The signal is still there for excluding the local group, but about, I think, a dozen or so intersections are with M33 and M31. And this just shows a figure from Xavier's paper from a couple of years ago where he shows the DM as a function of impact parameter for the CGM in blue, so individual galaxies, the intergroup medium in green, and the intracluster medium in black. And you can see that in the case of groups, below about 400 kiloparsecs of impact parameter, you get over 100 units of dispersion measure.
3 minutes, Liam.
Thanks. And here you can just see it on the sky. You can see M31 is really enormous in angular scale. And this is in line with more recent observations using other probes. So these are results using SZ and X-ray observations of M31 and the local group, where they find this really extended hot halo gas, larger than would have been predicted from M31 just on with its own CGM. And what you see on the top is the SCY parameter. And if you squint at the blue curve, you see it sort of tapers off. It flattens out like a top hat, and they interpret this as not a spherically symmetric intragroup kind of halo of 10 to the 13 solar masses, but instead as a hot gas bridge that connects the Milky Way with M31, so more cylindrical than spherical. And they find something similar in X-ray emission. Now, if you go by their estimates of the density and the sort of length scale of this bridge between M31 and the Milky Way, you find that the DM might be between 80 and 400 parsecs per cubic centimeter, which is in line with what we've seen through these DM measurements. And by the way, this paper is Chu, Huang, Bregman, and Li. Okay, to summarize, we found that CHIME FRBs that intersect foreground galaxies in the local universe have higher DM on average than those that do not. This excess DM is larger than expected in amplitude for individual galaxies CGM, and we attribute this to the fact that a number of our intersections are with galaxies and galaxy groups, and the intragroup medium can give you a lot more than a single galaxy. Another thing I'll point out is that this was done with 474 non-repeating FRBs. And so presumably CHIME has a lot more. And you could imagine that with a few thousand fast radio bursts, because the local group medium is so big on the sky, you could have 50 to 100 FRBs that intersect the local group. And you could really start to map out the local group medium, which is a very exciting prospect. So I'll end there and take questions.
Great talk, Liam. Super interesting. Okay, we have several questions coming in, so let's start at the top. From Shami, it says, very nice. Did you / could you try a galaxy mass dependent radius instead of fixed values of 150 to 250 kiloparsecs?
We actually did that. I shouldn't have skipped over that. I've tried both, where you just fix a virial radius at some value. But what I did for most of the analysis was I scaled that B-perp value by the expected virial radius based on the mass of the galaxy.
Okay, great. So next question's from Mohit. Liam, very nice result. Did you take into account non-uniform exposure and sensitivity as a function of RA and DEC of CHIME FRB in your jackknife resampling?
No, we didn't, although I can't think of a reason why that would skew or translate the DM distribution.
Yeah,
unless I do something.
The DM distribution maybe not, but maybe just the time on sky, and yeah, you might have a different you might have a different sky distribution, but yeah, you might want to discuss with Mohit on Slack. Okay, Susumu Inoue, have you tried looking at cross correlations with the SZ/X-ray results towards M31?
So that was what I was trying to highlight here, where we actually just sort of noticed this paper late in writing our own. So we haven't done a very direct comparison, but we just noted that the hot halo gas is more extended on the sky than expected, and that the DM contribution will be pretty large.
Yeah, okay. Okay, we're gonna run out of time for questions. Next, from Pawan, what is the average magnitude of the fluctuations to DM IGM for the two samples? The average DM host might be different for the two sets, and that would add to the error in the determination of DM CGM of foreground galaxies.
So you're saying that the host DM distributions could be different in the two subsets?
I think that's what he
Yeah.
means. Yeah.
That's possible, although I feel like it would come out in the wash, or it would show up if it had an effect on comparing the means of the DM distributions, it would show up in the jackknife test.
Yeah. Okay. Pawan, if that doesn't quite answer your question, you can ping Liam separately. And then I think we have time for, let's see, 2 quick questions. One from Ron. Have you made any correction for the halo of our galaxy, which may not be isotropic?
That's a good question. No, we didn't, and we probably should.
Okay, and then one last question from X. Great stuff. If you, I missed it, if you excluded the local group, what is the statistical significance in the signal?
Yeah, good question. So not as strong, although below 5% for B perps less than, I think, 250 or 300 kiloparsecs. So it's still there. But yeah, about half the signal disappears.
Right, okay. We might get through all of these then. Okay, we'll try a few more. One from Ray Lowe. Nice work with fantastic idea. How do you model the DM host distribution of the selected sample? Though there seems to be good statistical significance on the DM excess contributed by CGM, it's still more likely that the DM excesses are dominated by IGM and host.
Yeah, I agree that the DMs are still dominated by the IGM. But there should be no preference for the intersecting galaxies, or the intersecting FRBs, to have a higher local DM or a different local DM distribution than the other ones, because they shouldn't know anything about the positions of the foreground galaxies within 30 megaparsecs.
Right. And then last one from the chat from Nicholas. Could you explain again the high DM tail you see in the NFW profiles and what assumption you use to pass from dark matter to electrons?
Yeah, good question. Actually, this one was done by Vikram. I don't know why the MNFW has a fatter tail, or if this is just one of the one realization of it. But I think he would have just assumed baryon fraction of 80% of 15.7% or something like that, times the mass of the dark matter halo.
Nice. Yeah, and Vikram is probably on the line. If you, Liam and Vikram, want to discuss with Nicholas in the Slack, I encourage you to do so. Okay, thank you so much, Liam. Really nice talk. We'll move on to the next one in our session, which will be given by Tomas Cassanelli from the University of Toronto, who will be telling us about a VLBI localization of single burst with CHIME FRB Outrigger testbeds. So take it away, Tomas.
Yeah, thanks, Emily. Yeah, so I'll be talking about this exciting localization of this single burst FRB, not to repeat, with this Outrigger testbed and the ARO, or the Algonquin Radio Observatory telescope, this 10-meter telescope that we have there. I'm based at the University of Toronto. I'm supervised by Keith Vandergraaf. So a brief outline, what I'll be talking about today is the Outrigger testbed itself, a bit of theory of the very long baseline interferometry and how it's special for this wide bandwidth with CHIME, as well as the phase referencing and fringe fitting. Then I'll be talking about the event, this FRB that we detected a month ago, as well as the fringe fitting for the FRB, and finally the exciting results of the localization. So this is the telescope that we have at the Algonquin Radio Observatory, this 10-meter dish located in Ontario. So our baseline, and the baseline that we'll be using is, we have this telescope CHIME, as you know, it's located in British Columbia, and then we have telescope B, which is the located in the Algonquin Radio Observatory in Ontario, a radio quiet zone. And between these two sites, we have roughly a bit more than 3,000 kilometers. And with that, we get a milliarc second resolution of 30 milliarc second resolution theoretically. So what is the very long baseline interferometry? As some of you know, it's really similar to interferometry. We have our telescope A and our telescope B, and we have this certain baseline between those two, 3,000 kilometers. And then we have this source, and the source could be either our FRB event or a calibrator that'll explain why we need that later. But this source then emits this wavefront, travels through the ISM as well through the ionosphere and atmosphere of Earth, and then it gets detected in this first on our side A, and then later on side B. So why is that later? Is because there exists this delay, which is called a geometric delay, and it's really important in order to compute the localization of our object. And it's given by this equation here, equation 1, where we can relate the geometric delay respect to the baseline angle, which is here, but it's in terms, and can be a decomposition of the right ascension and declination of the object. So in order, if we find this, basically we're able to find the localization of our FRB. But of course, things are more complicated than that. In VLBI, what we truly measure is the total delay, and the total delay is polluted with a series of other delays, such as the clock, some ionosphere and instrumentational effects. With clock, I mean that there's 2 clocks different on each side, and each of them could be drift differently respect to each other, as well as the ionosphere. We're looking at through different parts of the sky, and the ionosphere has a high electron content that could affect these wavelengths, our wavefront. And finally, some instrumentation, and most of them are frequency dependent, as you see. So how do we do this is basically we have CHIME. This is up to scale at observing at 600 megahertz. And over here we have the ARO, the emitter dish, which is located at deck 22. This is in north and south, as you can see. So it covers only a small fraction of the CHIME beam. If we do a zoom in section, we see all the CHIME beam for beams inside of these white lines here. And when CHIME detects an FRB, it triggers a signal and tells ARO, don't erase that data, keep it, and then our semi-autonomous pipeline starts to correlate this event. So again, I want to say that again, that we are observing at deck 22, and we're fixed all the time with the telescope. So the telescope doesn't move. It's different than a traditional VLBI experiment where we track the object. In this case, we don't. We just see the object crossing our beam. And we're, of course, pointing towards 22 because of calibration purposes. In this case, we're observing the CRAP pulsar as our calibrator. So what is phase referencing? Well, phase referencing is it's useful for 2 things. One of them is that if I observe an FRB, I can reference that to my pulsar, my calibrator, given by a difference in the baseline angle, for example, or any other type of coordinate, right ascension declination. And also, it can remove some other things that we don't want in our total delay, such as the instrumentational effects. By doing that, it's simpler because we just compute the ratio between those 2 visibilities, the visibility of the FRB and the visibility of our pulsar and my calibrator. Yeah, so I'll repeat again that our project, this testbed and the CHIME FRB Outriggers project will be using pulsars as calibrators, at least in the initial stage, as my colleague Juan Mena already talked about that in his past talk. So after forming this normalized visibility, what we do with it is plug it in an estimator, and with a certain fringe model, we minimize that, and then we retrieve back our desired geometric delay, which comes as a constant from the minimization of this estimator. So, but what is the fringe model? I just want you to focus here on this equation, which is the equation of the phase, or the fringe phase model. And the phase basically depends on 2 things. And why we're interested, first of all, why we're interested only in the phase is because all the astrometric information is in the phase only. We don't care about the amplitude of the model or the fluxes, but only in the phase in order to localize the object. So this phase depends mainly on 2 things. This model, this fringe phase model, depends on 2 things. One of them is the differential DM, and this differential DM is basically done by the difference in ionosphere content on the 2 sides. On side A, on side B, will have a difference, as well as this constant differential tau. So this constant differential tau is basically related to some sort of residual of the geometric delay. So again, I take the normalized visibility, I plug it in my estimator as well as my model, I minimize that in order to find the perfect values for delta dm and delta tau, and then I take delta tau, and that tells me the localization of the FRB. So then it happened that a month ago we were able to detect this really bright FRB on CHIME. On CHIME was over SNR 100. Again, as you remember, has to be on deck 21, so we on 21, 22, so we can see it. And yeah, so it was pretty bright with the 500 DM units, and this was the pulse of it on CHIME, as you can see on the left, and on the right, it was the pulse, the same pulse again on the ARO meter, and it's not visible even if you sum along all the bandwidth of the 800 to 400 megahertz. And yeah, but nevertheless, it correlates. To do that, again, I need to form the visibility of this, and then I take all the slice around the pulse after the coherent dispersion on this side, and then I form the visibility. So now comes the correlation, and there's a lot of information here, so I'll try to explain this as best as I can. But on the left side, we have the phase of this normalized visibility, and on the right side, I have the Fourier transform of this visibility again. And this Fourier transform tells me it's an indicator of the correlation strength that exists between the two wavefronts. The first panel is a crab pulse observed a couple of days before the event happened, and the second panel corresponds to the FRB. The first panel is the crab pulse reference to itself, and the second panel corresponds to the FRB reference to this crab pulse. So you can see there's clearly a difference on lag here, and that lag difference will actually tell me the localization of the object. The third and fourth panel are just for competition, are other crab pulses that happen a couple days after. So what I do then, I just take a guess of the actual position, and I see that the phase start to wrap. Of course, before this, the phase was also wrapping, but it was wrapping so fast that I couldn't see it. But when I apply this phase correction to the phase or to the normalized visibility, I see that it starts to wrapping, but slower, and that's an indication that actually the correlation exists, and as well as I need to still correct for some of the things here in order to extract properly the geometric delay. So then how to do it? As I explained before, I take this estimator again, this chi-square estimator, and I plug in these two quantities, which is my fringe phase model, as well as the normalized visibility for the FRB. I generate this chi-square grid, and then I minimize for that value. And this is what we get. Of course, this is a really preliminary study. And yeah, so I calculate the minimum of this, and I estimate that and overestimate this error, which corresponds to roughly, I estimated 10 nanoseconds of this. Also, I was able to find the value of the differential DM between the two sides, and the differential tau, which contains again the geometric delay. So, the figure on the right side corresponds to a grid of array and deck. Each of these points again is a grid of array and deck. And then how I computed that is using this software, this great software, which is GFXCalc, and generates these delay models. And then I equate that value to the delta tau that I found from the fringe fitting. So after doing those equations, I'm able to retrieve back this region, which is a region in purple here, or pink, that selects the best estimate of the localization of the object. Forgot to explain here that we have, this is array and this is deck, and that the amplitude of this is given in microseconds. So this is a grid of points. Also notice that the grid of points also goes from one side to the other, increasing or decreasing on time, and that's because of the nature of our baseline. The baseline, as I show you, is like from west to east, and that only puts most of the restrictions will be done in the array instead of the deck. That's why the deck is so large. Nevertheless, the width of this is very small. It's less than 1 arc second, inclusively using 10 nanoseconds of error in the delta tau that I gave you earlier. So yeah, what we do next is take this value of this 1 sigma of VLBI and plug it in then in some, for example, a pulsar survey, as you can see here. This is on log scale. And on top of this, also I have to explain I have these contours, these ellipses corresponds to the localization from CHIME. CHIME, along with the baseband backend of CHIME FRB, we're able to localize this FRB. But of course, as you can see, there are many other galaxies inside these regions of 1, 2, and 3 sigma. But on top of that, I'm able to also to plug in the VLBI localization of one sigma that I found. Again, you can see that there's not many galaxies here that are overlapping in the same field that overlaps the VLBI and the CHIME. And it's also important to notice that these two are two independent methods.
3 minutes, Tomas.
Yeah, thanks. And then I do a zoom in of this region. And yeah, so basically with this, I just want to say that I don't claim that this is actually the galaxy. There's still some tests that we need to do in order to actually confirm this, but it's really preliminary result, but it's pretty exciting. And we're confident that these contour lines are really robust and independent. So that's a pretty good sign for us. And yeah, so an in-depth analysis is coming from this first localization from this testbed. Again, all this development that has been done, it's the basis for our next project, which is the CHIME FRB Outriggers that will come soon. And I also pasted the properties of this potential host, which is this galaxy. My colleagues Mohit and Ryan helped me calculate these values, that there's an excess DM, for example, and also an excess in the RM. And yeah, so the next steps is to cross-validate these results. We're going to make sure that and going to reduce basically, because I overestimated this value of the delta tau from this minimization procedure in the fringe fitting. And as well, we are waiting for more FRBs to come in this overlap field of view with the testbed and with the upcoming outriggers. And also, if you want to know more about the method of fringe fitting, since it's complicated to explain this such a brief period of time, it's all explained in the recent paper that I submitted, as well explaining the paper of my colleague Calvin. So yeah, thanks.
Really great stuff, Tomas. This is such a beautiful picture. Okay, we have one question already, and I'm sure more are coming. So the first one's from Adam Deller. What is the estimate of the uncertainty of the term delta tau clock, and how was that estimated? And do I read correctly? Do I read correctly that the 1 sigma uncertainty of the CHIME only baseband data is about 10 arc seconds?
Yeah. Well, depends on if it's array or deck, but it's usually it's less than 1 arc minute on the CHIME side. And how do I estimate the clock? Well, that's I have a backup slide for that actually. Yeah, so how do I estimate the clock is using crab pulses between several days. I compute several crab pulses, correlation before and after. And by doing so, I'm able to trace this line, which is the drift that exists between the two masers. Well, we have a maser at ARO and the clock at CHIME, and then we estimate this drift, and then I subtract that drift from the actual measurement of the FRB. So that's the reason why also in this picture over here, yeah, this one. So there's a trend of the crab pulses that exists there. It's also in the paper I submitted. It's also there a bit more better explained how to subtract that drift.
Nice. Okay, I have a question actually, which is so for your plot that you showed with the localization with the baseband and then the ARO, what kind of constraints? So say there was like a third baseline, or sorry, a second baseline, a third telescope, like for the CHIME, like looking forward to the CHIME Outriggers. What would a second baseline give you? What would that kind of look like on this plot?
Yeah, well, depends on where the baseline is located, right? But if it's lower south or north, that will help us a lot. So we could have another one of these lines plotted on top, or we could use a 3 baseline combine the three visibilities basically to include some other effects. I haven't thought much about that, but it'll be really easier in order to localize actually the galaxy if we have another contour of those. Yeah, it could be a trace.
Yeah, that'd be nice.
Basically,
yeah.
Hopefully.
All right. Any other questions? Yeah, I guess I had another one, even though I know like this has been talked about a lot. In terms of the like rates for something like this, so I mean like the ARO 10 meters only looking at a fixed deck relative to the whole field of view of CHIME, and there's just this one extremely bright FRB. But sort of like rate wise, is this something that you with this baseline established, something that you would expect that CHIME and ARO would see together somewhat regularly?
Yeah. So do you mean the change of the baselines over time? I guess.
Well, I just mean like in terms
of
rates for like how many FRBs might CHIME and ARO see like this per year or something.
Oh, right. Yeah, so we've seen many other FRBs on the sheer field of view, but unfortunately, I haven't been able to correlate them. I thought something was wrong with the system, maybe, but we really need a really strong FRB in order to correlate. After we got the SNR 100, I was able to correlate it in a couple of minutes, and I realized that everything was working. It was just the fact that we didn't have the strong SNR, and also we know the pointing of the 10 meter, but only based on our sources, the graph pulsar. Yeah, but we've been getting many, and as well as we observe also the magnitude in 2020 with the ARO 10 meter.
Yeah, great. Okay, if there are other questions for Tomas, please ask them over in the Slack channel. We'll move on to our next talk. So very nice talk, Tomas. Okay, and then our final talk of this late breaking news session is a live talk by Pravir Kumar, who will be telling us about generalized Faraday rotation in Park's ultra-wideband low observations. So take it away, Pravir.
Thank you, Emily. Hello, everyone. So I am Pravir. I am a PhD candidate at Swinburne University, and I'm going to present latest FRB results with the Parkes Radio Telescope. So at Parkes, we use the ultra-wideband low instrument, which provides a continuous coverage from 700 megahertz to 4000 megahertz. We record the data at 64 microsecond resolution, and at a frequency resolution of 0.5 or 1 megahertz. The data is coherently redispersed in order to minimize the channel smearing. And in order to search this huge bandwidth of data, we follow the subband searching approach, where we divide the data into smaller chunks of subbands, and we search each of these chunks independently. So to search the data, we use the standard single pulse searching tools, Heimdall, and the neural net classifier fetch. So ultrawide observations are important in order to characterize the spectral features of not only fast radio burst, but also pulsars. And usually this is achieved by using multiple simultaneous observations with different telescopes. But with UWL, we can do this using one single instrument. So we have been observing or monitoring several repeating fast radio bursts, and we have detected multiple repetitions. So here I show some of the examples of repeat bursts from the source of 18031A and 2011-24A. So almost all the bursts that we see with UWL are band limited, and some are quite narrow, and they vary in their properties. So we do see bursts with temporal width of 100 microseconds, and we also see bursts up to 40 milliseconds. So 2011-24A is a new repeating source. discovered by CHIME earlier this year. And this is the second closest known repeating source. This source showed high activity earlier this year during April to May. And we did monitoring of this source in the first week of April with ASCAP and PARCS. So with PARCS, we detected 5 bursts in 1 hour of observations on 5th of April. All the bursts we found are band limited, and the delta nu by nu varies from 0.1 to 0.4. The dispersion measure that we obtained from these bursts has a large deviations. And so the mean or the weighted mean DM that we obtain is 413 parsec per centimeter cube, which is in agreement with the DMs reported by other teams. So all the UWL bursts that we see from this source are highly polarized. We obtain a rotation measure of minus 613 radian per meter square. The linear polarization fraction varies from 0.5 to 0.9. And in one of the bursts, PO3, we see a significant amount of circular polarization to be around 17%. And this looks similar to what have been reported in other circular polarization in other bursts from the same source in the Effelsberg burst in Hilmarsson et al. And in the next burst, PO4, we don't see any circular polarization, but in the 5th burst, we see a high amount of circular polarization. We also see large variations in polarization angle in this burst. So taking a closer look at this burst 5, we find that the optimized dispersion measure for this burst is 418 parsec per centimeter cube, using both the approach of maximizing signal to noise and the structure. Now this deviates from what is the average DM from this source, and we interpret this as a DM axis. So at this DM, we see that the burst clearly has 2 components, and they are separated in time. And the RM that we measure for both the components are consistent with each other, which is minus 618. We do not see any circular polarization in the component 2. And in the component 1, we see it to be 50% circularly polarized, which is quite high. So in order to confirm the dispersion measure, we look into the other Stokes component of this burst, and we only take the circular component into consideration. And so using the Stokes V and optimizing the structure of only Stokes V, we find that the DM is also 418 parsec per centimeter cube. And so this clearly suggests that, and we also don't see circular polarization in the other component in the V spectra. So this clearly suggests that there's a significant deviation in the DM for this burst, which is 5 parsec per centimeter cube. So taking a more detail about how we determine the rotation measure. So when a radiation passes through magnetoionized cold plasma, the plane of linear polarization rotates, and it's proportional to lambda square, where lambda is the wavelength. And this is characterized by the rotation measure, or RM. And so to determine the RM, we use the standard RM fit approach, where we do a grid search for RMs. And we also, additionally, we use RM nest, where we directly fit the Stokes Q and U using a Bayesian approach. So we find that the RM measured from both these methods are consistent. And the best fit is shown in this plot. So how do we explain the circular polarization? Is it intrinsic to the source? Theoretically, it is possible to have a small amount of circular polarization in this intrinsic circular polarization in the synchrotron emission. But such a high amount of circular polarization that we see in this burst, and the circular polarization having a frequency dependence, cannot be explained using a simple model of synchrotron emission. And so another possibility is whether this is due to propagation effects happening within the source. So in order to consider this possibility, and so we model the derotated Stokes spectra along with Stokes V using a generalized form of Faraday rotation. And we find that the model very well describes the Stokes data. So a generalized Faraday rotation, or a GFR, happens when the propagating medium, the natural wave modes in the propagating medium are linearly or generally elliptically polarized, and not circularly polarized, which happens in the cold plasma, which causes the ordinary Faraday rotation. So, and the rotation of the polarization vector can be constructed in an analogous manner as the ordinary Faraday rotation, but this time with an arbitrary dependence on the wavelength. And so we use this GFR model, and we fit directly to the normalized Stokes Q, U, and V. And we consider rotations along both the Stokes U and V. So we find that for alpha equal to 3, this model fits the Stokes spectra very well. And we obtain a GRM, or a generalized rotation measure, of 39 radian per meter cube. The units are in cube because the alpha is 3. So to understand this generalized Faraday rotation, one can visualize on a Poincare sphere, so which consists of the 3 axes are the Stokes Q, U, and V, and an ordinary Faraday rotation is a rotation of polarization vector along the V axis as a function of frequency, at a constant latitude on the Poincare sphere. Whereas a generalized Faraday rotation happens so the generalized Faraday rotation happens by taking rotation at any arbitrary point on the sphere. And so we have to consider rotation along another axis as well. And in this kind of rotation, the linear polarization gets converted into circular polarization. And it has already been established that a relativistic plasma can cause such a rotation with a lambda to the cube dependence. And in this case, the GRM is known as relativistic rotation measure, or RRM. So, and an ideal candidate for such a scenario is an electron-positron pair plasma. And assuming that both have the same distribution in such a relativistic plasma, they both cancel out the circular polarization, the intrinsic circular polarization, and so intrinsic circular polarization will be 0 in this case. And all the circular polarization can be attributed to this GFR. So we assume that in such a scenario, the relativistic particles dominate, and all the wave modes are linearly polarized, and this follow lambda to the cube. One can calculate the RM and one can establish the relationship between RRM, which is the relativistic RM, and the perpendicular magnetic field strength. So here we assume that a power law distribution of relativistic particles, and since we have observed DM axis in this burst, we infer that this DM axis is due to this electron-positron pair plasma, and using that DM axis, we then calculate that the perpendicular component of the magnetic field will be 0.02 Gauss for a minimum Lorentz factor of 1. So we show here that the circular polarization observed in this burst is consistent for radiation propagating through a relativistic plasma around the progenitor. So in the end, I will show. In the end, I will talk about the emission band switching observed in this source. So this is a timeline of all the 5 UWL bursts that we detected, along with other bursts reported by different telescopes in the same time frame. So we have bursts. Yeah, thank you. So we have bursts from CHIME, UGMRT, and ASCAP. And we can see that the error bars are the spectral coverage of the bursts. So assuming that all the bursts are narrowband, we see that the emission band, or the central frequency of the emission, switches to a different frequency on a time scale of a few hours or few minutes. And we have seen in other repeaters, particularly R3, that this is related to the frequency dependence is related to the activity window, but we do not have a periodic determination for this source yet. And so more observations for this source will be determined if there is an evolution that across frequency that we see here. Another example that we see is in the case of 180301. So here are two bursts which are detected within 50 minutes in time. And we see that the first burst, B13, is 20 millisecond wide. It has multiple drifting components. And we clearly see an example of sad trombone effect here. But the next burst detected just after 50 minutes is at a completely different band at 1.8 gigahertz. And it's a very narrow band burst with a width of only 100 microseconds. We see no polarization in the B13 burst. However, the second burst is highly polarized, highly linearly polarized. Also, we determined that the rotation measure that we determined from B14 burst is minus 140 radian per meter square, which is completely different from what the FAST reported for the burst from the same source 2 years ago. Another point here is that many observatories would have missed one or the other burst simply because of their limited bandwidth. So in the end, I'll summarize my talk. So we showed here that the emission band frequency switches on a time scale of hours, and it is yet to be determined if this relates to any periodic modulation. We showed here that repeating FRBs have diverse polarization properties. We see circular polarization fraction as high as non-repeaters. We see linear PS swings similar to 180301. And so now we cannot use these polarization properties to discriminate between repeaters and non-repeaters. We show here that the circular polarization can be explained by a generalized form of Faraday rotation, where the linear polarization gets converted into circular. This is consistent with propagation through a relativistic plasma near the light cylinder. And since we do not see a circular polarization in most of the bursts from this source, it suggests that this is a rare phenomena, and so we do not see, that explains why we do not see circular polarization in all of the bursts. So I will end my talk here. Thank you.
Really, really interesting stuff. All right, we have a few questions coming in already. So the first one from Vikram says he has several questions, but here are two. Feel free to choose one or both. So his first question is, what was the rough time scale over which the DM excess was observed? That is, were there bursts on either side with a lower DM?
So we had 5 bursts with UWL, and we had 11 bursts with ASCAP across the first week of April. And well, all of the bursts show deviations from the average DM. However, when we take the structure maximization approach, we found that the DMs are consistent with 413. However, for this PO5 burst, this is the brightest UWL burst that we have seen. And yeah, and from both the approach, we find that this has a larger DM. And so we find that the evidence is strong enough to consider that there is a DM excess.
Great. Okay, and Vikram's second question, how do you reconcile the low RM with the high B perpendicular implied by the RRM?
Low RM, low. So RRM we obtain is around 39. So a low RM means, and the RM we corrected for is minus 618. So I don't understand how the question.
Vikram, you want to, let's see, if you want to speak up. Okay, Vikram says he'll follow up on Slack, which is perfect.
Yeah,
So
sure.
I'm going to try to unmute him, but that sounds better. Okay, the next question is from Paz, who says, very interesting. In your modeling, what is the spatial extent over which this large magnetic field persists?
So our modeling does not consider the magnetic field. The modeling is just based on the Stokes components, and which is using the approach of Poincaré sphere. The magnetic field we obtain is using this inference of how the relativistic rotation measure can be if we assume that the relativistic particle dominates and there is a power law distribution. And this is analogous to how the Faraday rotation measure is calculated for that. So, so the value that we obtain for GRM is should be independent of anything related to magnetic field.
Yeah. Okay. And then one more question from Ron. Does the frequency to the -2, the frequency to the -2 cold plasma DM apply for the relativistic plasma needed for generalized Faraday rotation?
Frequency to power 2, you mean like the regular dispersion measure relation?
Yeah, I think so. So I mean, because to get the generalized Faraday rotation, you have to have some like more extreme, or I guess more relativistic plasma. So would that deviate from the cold plasma frequency of the -2 DM relation?
Yeah, we haven't considered that effect yet, and since this is still a work in progress, so but yeah, I'll have to check that. Yeah.
Okay, great. Okay. 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 Are there any further questions? Don't see anything on the Q&A yet. So okay, then we will finish up. Thank you, Pravir, very interesting talk. And thank you to all of our speakers from this session. So if you didn't get your question answered or you have more questions after this, please feel free to post them on the Slack channel. And otherwise, we can conclude the session a little early. And I hope that if this is your last session that you're joining in FRB 2021, I hope that you enjoyed the conference and that you found it interesting and useful and stimulating and inspiring for your work going forward. And if you are able to, we have the second session of the late breaking news, this same program, but 12 hours later, happening in the 2A session, or sorry, the 1B, getting it flipped around, in the 1B session for late breaking news. And there we will conclude the conference. Jason will wrap things up, and we will have also some special thoughts from Jocelyn Bell-Burnell, who will be joining us on that call to also give us some of her thoughts and highlights from the conference. So I hope you're able to join us then. And if not, I hope you'll check out that recording afterwards. So thank you very much for attending tonight and or this morning, wherever you are. And we'll hope to see you again sometime soon. Thanks, everyone.